So before we get into this we're going to draw like these vectors and velocity graphs, but just kind of hold on to, I guess, the plan that we're going to have. So I drew some notes, but let's go over it again so you just kind of see where all this stuff is going to go. All right, so we're going to draw Okay, so first we draw the simplest sort of case of a pump with an impeller and think about how the fluid will flow based on these parameters. So this right here involves most of the assumptions that go into getting an analytical graph for what your pump characteristic curve is. It's totally wrong. It's never going to work, but it's an analytical approximation as a first step. Then you get to actual pump curves. But that is all going to come from how you idealize what the pump is based on these parameters. So that's kind of hard. But once you have that picture, then the step 2 is you add some math at it. So you throw math at it. Or essentially what you're doing is you're going to conserve angular momentum. So this is something we haven't done in this class because you always forget about angular momentum in physics when you're an undergraduate, but it's another conservation equation you have to get some equation. All equations in physics come from a conservation equation. So this is a forgotten cousin. Okay, so after you get that equation, right, then you're just going to rework the variables, right? You're going to rework the dimensions and everything like that to get an expression for the head loss of the pump as a function of the flow rate. So this is sometimes called ideal, or A for actual. I don't really care about the subscripts, right? Because head's head. So right, step 3 is you take that conservation equation, you rework the units, and you do some equating of other things to get this function. Now this function's wrong, and that's why I usually put the subscript ideal, but it doesn't matter. That's where we're going to end with this ideal. Okay, what else do we have? The last step, or essentially for past this lecture, is you then take this idea of what this curve looks like, and then you turn all these expressions into just sort of pump. And this is the biggest takeaway from this entire section is you get this pump performance curve, and then you get these, right? You get these ideas, analytical or experimental, and you can make curves that are going to characterize how your pump performs based on the flow rate that it's working at. And there are a ton of these curves. There's efficiency curves, there's characteristic curves, there's a best efficiency performance curve, but they're all on the same type of plot. So how to interpret these plots and use these plots is the most important part of this section, I would say. It's what your whole project actually is going to be doing. But we got to get there so you at least know where all those equations come from in the first place. But if you just skip ahead to this thing, I think you'd have a hard time because it's easier to understand or just judge yourself. Essentially, if you use this ideal equation, which is analytical, and sometimes you have the variables for it, you can get a sense of what your pump's going to do, even though it's not actual. But that's the plan for what's to come.